Hello, and we are going to be solving these problems. This is called for some reason half Atwood machine. The pulley has zero moment of inertia, and then we are going to solve it again with the pulley having moment of inertia. First, the shortcut to solve this problem is to treat this like a system, and the external forces of the system is m gravitational pull on object 2 and friction, kinetic friction. And the tensions, because there is no moment of inertia on the pulley, there is one tension, is an internal force that cancel out. So this can be thought as this, and the pull over here is M2G, and then the friction is here, there. So you got negative Fk plus M2G, because it's a system, you are pulling two masses. This is the acceleration of the object, and then the normal force over here and 1G over here. So friction is mu K normal force, and the normal force is M1G. And the acceleration of the object is G, common factor, mass 2 mu K S1 divided by the sum of the masses. I personally don't like shortcuts. I don't like to treat this like a system, because it's better to have Newton's second law on object 1, Newton's second law on object 2, especially when you move to a more complicated problem. These shortcuts and treating the two blocks as a system becomes a liability. So how you are supposed to do this, you always divide the object in M1, and forces acting on M1 is friction. I'm not M1 gravitational pull, normal force, and tension. And on object 2 you got tension and M2G. Now, so you got this A1, and here you got T minus gravitational pull on object 2 equals M2A2. And because they are connected by the length of the rope, the accelerations, and this is interesting, I'm going to put my axis here, and you're going to see why later. So the length of the string is constant, and because the length of the string is constant, let's call it L, is this piece over here that is x1, and this piece over here that is x2, I mean y2 for the object. And if you do the first derivative of a constant is 0, so this is b1 plus b2. And if you do another derivative, the derivative of the position is the velocity, the derivative of the velocity is the acceleration. And you get that A2 is opposite to A1. And if we call A1 A, this is minus A. So here, because it's not a system, I need to prove what the accelerations are. So let me put over here mu gate m1g plus t m1a, and over here plus t m2 negative a. And now I will multiply this one by -1. So this is my system of equations. I will put the tension first and then the friction, and this is my second equation. I multiplied this one by -1, that's why I switched the signs over here. I just added up term by terms and this cancel out. Let's put the positive number first. So acceleration is this. Usually if you're doing this lab, again, if this is a physics problem, usually it's being asked what is acceleration, and then if you have acceleration you can find the motion of the object by the kinematics equation. But usually when you have a lab, the objective in the lab, in the experiment, is to find the physical constants of the equation, that in this case is g, and the coefficient of kinetic friction and the acceleration of gravity. So how to manipulate this equation such that you get that? I think in this case you usually measure the acceleration by putting a motion detector here behind the block or down here, either way. Or you could measure the acceleration of the pulley here if you had the what is called the smart pulley that has spokes, and by knowing the width of the spokes you can find the acceleration of the pulley, which is the acceleration of the object as well. So you need to manipulate this equation in such a way that if you measure the acceleration, obviously you can change the masses in order to find g and mu k. So in that case we multiply by m1 plus m2 the way it was over here, this one over here, and then you have m2 g minus mu k m1g, and then I'm going to divide by m1, everything by m1. And why I did that? I did that because now if this is on my y-axis, again the acceleration is measured with the motion detector. You get velocity versus time. And you get 100 points per second, and the slope of the velocity versus time graph that you get from the motion detector is going to give you acceleration, and then you vary the mass. This is going to be your y-axis for the linear fit. But look what we got over here. Over here we got the acceleration of gravity as this positive, and it's going to be the slope, and the y-intercept is going to be negative, and it's going to be the coefficient of friction times g. This is the y-intercept. So this is the graph that you are going to do on the experiment. Acceleration what goes over here. And here you're going to put 2 and 1. This is units left, and this has units of acceleration. So this the y-intercept is negative. It's going to be somewhere over here. Mu kg is the y-intercept, and the slope is going to be g. So the negative mu k, the coefficient of friction times g, is the y-intercept, but the acceleration of gravity is the slope of the line. So mu k is the negative y-intercept divided by the slope of the line. Remember, from the theta line you get the slope and the y-intercept. So the acceleration of gravity is the slope, and the coefficient of friction is the y-intercept divided by the slope. See, so this is the typical lab that you do by putting the motion detector behind the block or under here, and then you vary the masses. So this is a hang mass. You put different slots of masses, measure the motion, the velocity versus time graph. From the velocity versus time graph you get the acceleration. You make this graph, this linear regression graph, and from there you compute the physical constants of the experiment that are the acceleration of gravity, the magnitude of the acceleration of gravity, and the coefficient of kinetic friction. Alright, so now in this problem over here, there is moment of inertia, so I draw a bigger pulley over here. So the moment of inertia is not 0. In this case, you have the same constraint over here. You are going to get that A2 is -8 and A1 is A by the same constraint equation that the length of the string is constant. And I'm going and there is another one that the pulley is not slipping, so the rod, the string over here is not slipping. So if you measure, if the pulley moves, the string moves delta x, you got exactly delta theta over there that is going to be related to the displacement of the rope or a string over there. That translate into then you get that delta theta is delta x by r, and if you do the seconds, the first and second derivative, you get that the angular velocity is velocity over r, and angular acceleration is linear accelerations divided by r. So this is the situation when there is no slippage. So again, since there is no slippage, if there is no slippage, then the angular acceleration is the linear acceleration divided by the radius of the pulley. Because the length of the string does not stretch, L is constant, you get that the accelerations are a -8. Again, why negative? Because again, I think I'm going to put my axis over here. So this block is moving down and this block is moving to the right. So now we are going to do exactly, this is why treating this like a system, as the shortcut that we did over here, it doesn't work. That's why shortcuts are bad in the sense that you see it or not, but if you always follow the procedure of putting the Newton's second law in the x and y axis for each object, in this case you are supposed to have 4 equations. Y axis, That is trivial because there is no motion in the y-axis. Here there is no motion in the x-axis. And so those two equations are out. But then you have motion on the x and motion on the y. By the way, the motion in the y is not out because that's how you find the normal force. So here the normal force is m1 times g. So this is an equation that is going to be used when we use coefficient of friction. So it's mu k m1g. So the equation in the y-axis for block 1 is used. That's how we get this one. But I'm going to skip it over here. So now x-axis for this one, we got negative friction. And now you got two tensions because you have the pulley. So this is going to be T1 and this is going to be T2. So plus T1 acceleration. And for the other object, I got T2 positive 2g, and I put negative acceleration over here. What is A? Is the magnitude of the acceleration of either object. But this is a vector equation, so directions matter. And now we have the pulley here. So T2 is here, T1 is here, and T2 is here. And now we have to use the torque equation. Remember that counterclockwise is positive torque and clockwise is negative torque. Keep that in mind. So the equation, so T1 is going to spin it this way, so it's going to be counterclockwise, so T1 is positive times R, and T2 is spin clockwise, so it's negative T2 R, moment of inertia times alpha. But how is it spinning? Alpha is this way, right? Because this block is moving down because of gravity, so the pulley is moving this way, and that is negative. So alpha is going to be negative A over R. It's very important. So this equation is plus T1 times R, T2 times R, I negative A over R. So I'm going to write these equations over here. So the first equation, I just substitute the friction as this plus T1 and 1A. 2, I'm going to multiply by negative 1. So I got M2G minus T2 equals M2A. I just multiply this one by negative 1. And the last one I'm going to be dividing by R. So it's T1 minus T2. T1 minus T2 equals, let me put the negative, I over R squared. That's my third equation. But because I'm adding these two, 1 and 2, I will write 3 like it is over here. T1 minus T2 equals negative I R squared times acceleration. Alright, so now I'm going to add 1 and 2. So 1 plus 2 is going to be, I'm putting the positive number first and then the negative. But T1 minus T2 is this. So I'm going to put this over here. And I get M2G. So I'm going to move the acceleration term to the other side. You get m1 m2 plus I over r squared, common factor a. And this is important because remember the moment of inertia has units of kilograms meter square. So moment of inertia by square of the distance has units of mass. So you could call this as m star if you want, because that has units of mass. More on this later because we introduced the moment of inertia. That means there is another physical constant in the problem that is going to be the moment of inertia of the pulley. You could treat it like a cylinder, but usually the pulley has spokes and has a bearing. So it's better not to try to find the mathematical expression of the moment of inertia of the cylinder. That is 1/2 mass r squared. I think it's better just to treat it like I, and I is an experimental constant that we introduced. So now we got 3 experimental constants: the acceleration of gravity, the coefficient of kinetic friction, and the moment of inertia of the pulley. Or this constant m star is the ratio of the moment of inertia by the square of the radius. And this is going to be your experimental constant. I'm going to leave it like that for convenience, but I usually treat it like m star. So my acceleration is now, I take g common factor, m2 mu k 1 over m1 plus m2, and now we got these extra terms over here. Now we got these extra terms over here, and again, if I is 0, if you ignore the moment of inertia, you get this case. And it's going to be less acceleration because you have to see it more like an energy. It's easy to understand this in terms of energy. So it's this gravitational pull is creating the energy that move everything. But now you are moving the pulley and moving M1. So it makes sense that it's going to be less acceleration than in this case because the pulley has a mass that is now rotating. In this case, the pulley mass that is rotating is ignored, so you get a bigger acceleration if you ignore the moment of inertia. Now, experimentally speaking, if remember that in this case we got this equation over here, and here there is no way to linearize it, so always remember that a linear regression is only going to give you 2 parameters, the slope and the y-intercept. But over here you got 3. You got acceleration of gravity, coefficient of kinetic friction, and I over r squared. So you could do it by doing non-linear fits, and you could find the 3 parameters from the data. And what is the data? You usually collect acceleration, m1 and m2, acceleration m1 and m2, and you determine experimentally, you determine g coefficient of friction and I over r squared. This is something I've been trying to do in the past, but I haven't been successful unless I use a nonlinear fit. Again, these are the 2 equations with moment of inertia, without moment of inertia. Here the pulley is considered, the mass of the pulley is rotating. Here the rotation of the pulley is ignored, and in both cases the length of the string does not stretch and there is no slippage. There is no slippage.